Hello, welcome to the NYU Tandon School of Engineering and this semester's final presentation in our seminar series in modern artificial intelligence. The series is aimed at unifying scientific communities around the influential research ideas of today that we predict will have a major impact tomorrow. And we hope that the discussions that result here will promote groundbreaking discoveries and contribute to build a better world. I would like to thank Dean Jelena Kovacevic for her strong support, as well as my own Department of Electrical and Computer Engineering for hosting this series, which has evolved since its launch into a respected and significant event in the AI world. When I first conceived of this series, I hoped that I would be able to attract highly esteemed speakers doing revolutionary work in their respective fields. I've mentioned this before, and I'll say it again with some humility. I've succeeded beyond my wildest dreams. The neuroscientist Joel Davis once described the brain as the last and greatest scientific frontier and an eternal cosmos. He asserted, the more than 100 billion nerve cells and trillion supporting cells that make up your brain and mind constitute the most elaborate structure in the known universe. Our esteemed guest today, Samantha Wood, has spent her career exploring that scientific frontier and advancing our understanding of how that elaborate structure learns to build perceptual and conceptual knowledge. Her research focuses on how newborn brains learn to make sense of the world. What algorithms allow brains without prior experience or instruction to convert streams of high-dimensional sensory input into knowledge and adaptive action? Using tools from AI, she formalizes theories from psychology and as agent-based models that use deep neural networks to perform the same task as humans and animals. By simulating the development of intelligence using artificial agents raised in realistic virtual reality worlds, she aims to build predictive, integrative, and embodied models for psychology and neuroscience. Samantha is currently an assistant professor in the informatics department of the Luddy School of Informatics, Computing and Engineering at Indiana University in Bloomington. She received her BA from Harvard University in Social Studies and her MA and PhD from the University of Southern California in psychology, with a focus on brain and cognitive science. Her presentation today is entitled Reverse Engineering, the Recipe for Object Perception, and she will be discussing an integrative framework for linking the study of artificial and biological intelligence. Without further ado, I give you Samantha Wood.
Hi, everyone. Thanks so much for having me today. I'm really thrilled to be able to tell you about my research on reverse engineering the recipe for object perception. Get Zoom to cooperate with me no matter what I do. Somehow, some way. All right. Perfect. Now, broadly speaking, my research is centered on what I would argue is one of the great unsolved mysteries in science, which is what are the origins of intelligence? When we're born, what kind of mechanisms exist in the brain that let us make sense of the world around us? And what prompts us to seek out some experiences for learning over other experiences? How does our brain become shaped by these experiences? And what are the learning mechanisms that are present in newborn brains? In the words of Richard Feynman, what I cannot create, I cannot understand. And that means that in order to understand intelligence, we have to try to reverse engineer it. And that's exactly the work that my lab does. In order to reverse engineer intelligence, we use a parallel controlled rearing approach, where we perform parallel controlled rearing experiments on newborn animals and newborn machines. On the animal side, we have built automated controlled rearing chambers that use virtual reality to present different types of visual worlds to newborn animals. You can see a picture of one of our chambers at the bottom here, where the walls are actually screens or monitors, where we can pipe in whatever kind of visual worlds that we want to be able to test our animals on. And at the top, you can see one of our newborn animals, a newborn chick, who's being reared with this artificial object shown on a screen and is completely believing this illusion that we've created. Now, we can actually use these benchmarks of animals, newborn brains that are raised in these really sparse visual environments, as high precision benchmarks to test artificial intelligence models. And to do that, we've created a digital twin of our controlled rearing chambers in a video game engine called Unity. We then create artificial brains, which we can put into these artificial chip bodies to move around the chamber and collect the same kinds of experiences that the chicks in our actual experiments in our physical chambers experience as well. And by using artificial intelligence, we can take these models and have them be falsifiable theories or computational theories of how learning actually works in newborn brains. So this is very much a symbiotic relationship between artificial and biological intelligence. But what's critical here that I want to take note of right away at the start of this presentation, and what makes this so different than other benchmarks that you may have seen from humans or from other animals, is that because we are using controlled rearing from birth, we're actually able to make sure that the newborn animals and newborn machines are receiving the same training environments and are tested on identical tasks, which is not possible otherwise. So here I'm going to be focusing on one particular cognitive ability, even though we've looked at other things in our lab. I'm specifically going to be focusing on object perception. And I want to take a step back just to potentially persuade you as to why object perception is such a fascinating feat. I'd like everybody to look at this picture and think about what you see in this image. What kind of entities do you see here? This image is made up of a series of different regions of different luminances, different hue values. And yet, despite that, we're able to actually carve this image apart in our visual systems into meaningful object entities. And probably all of you come up with something like this, right? We've got walls and doors and floors and dancers and bagpipe players, apparently. But you probably all come up with a really similar way of parsing apart this visual input. Even though this feels so effortless and easy to us, it's still not entirely clear how we do this in our brains computationally. Because if I were to actually show you, for example, all of the different regions of hues and luminance in this image, it looks more like this, which is not all that interpretable, right? It's not clear what we're looking at here. So this is a really hard skill to know how we can actually take all of these varied different regions together and form them into meaningful object percepts. And let me just indulge me with one more example. So here's one image of an object. I won't say what the object is, but probably most of you can guess. And I'm going to give you all a job for this talk. So your job is going to be, I'm going to show you two new images, and all you have to do is tell me which one shows us the same object. Don't worry, it's not a trick question. So we've got our original image, and here are two new ones, the top and the bottom. So we're just going to do a quick straw poll by show of hands. Who thinks the top image shows the same object as our original? How about the bottom one? Show of hands for the bottom. Okay, that feels pretty unanimous. And again, probably feels laughably easy to do, but this is really hard computationally. And the reason this is so hard is that if you look at the actual pixel space, what's actually shown on your retina, this top picture of a scooter is much more similar to our original bicycle image than the bottom image of the bicycle just shown from a new viewpoint angle. So how are we doing this? How are we taking this retinal space or this set of pixels and being able to translate them into meaningful objects? In other words, how do we learn to perceive objects? Now, as I mentioned before, I turn this into a reverse engineering perspective. So I want us to all engage in a thought experiment together today, which is I want us all to imagine that we're creating a brand new creature from scratch. And we want to be able to build object perception into this creature. And so for those purposes, I want you all to meet Pip, who is a brand new creature I created using ChatGPT and DALL-E. And the idea here is that I want us to imagine that we're creating Pip from scratch. We're going to build him from the ground up in order to give him object perception. And the question becomes, what ingredient then do we need in order to reverse engineer object perception into our little friend Pip here? To make this a tractable question, I'm dividing this up into 4 different possible ingredients here, which are training data, brain architecture, our objective function for how this brain architecture will actually learn, and a body as well. Let's start with our training data. One philosophy you'll see me come back to over and over again in this talk is the philosophy of, inspired by Occam's razor, if you will, which is how little can we get away with? How little do we actually need to build into this in order to still have object perception function? So let's start with the least training data I can imagine, which is nothing. What if we give him no visual experience ever and then ask, can you actually recognize an object now given no visual training? Now, this is really extreme, but there's actually data on experiments that have been done on blind patients who have recovered sight that can help us answer this question of what does object perception look like at the very, very onset of vision. Researchers from MIT worked on a project where they removed cataracts from patients who had congenital cataracts so that they could see for the first time. And then within minutes of gaining their sight, they would ask them to do different studies on object perception where they would have to parse or segment different types of visual input. And these studies of blind patients can tell us how object perception operates without any training data at all. So I'm just going to show you a brief clip of one of these patients, and they're asking him about what he's seeing on these screens, how many objects for the first time.
His visual-motor coordination is quite poor, but you get a general sense of what are the regions that he's trying to trace out.
I don't think we have any audio here, so I'm going to narrate for you. He's being asked how many objects there are, which you can probably tell from the subtitles here. And what he's going to do here is actually over-segment it. So he's looking for every chunk, whereas you and I, we would probably all say it's a square and a circle, it's just two. He's saying
and that's what's indicated in the green outline.
This is really common when they're asked to segment real natural images. This is the kind of segmentation you do, so they don't just see a cow, they see a black chunk, a white chunk, a black chunk, a white chunk, a black chunk, a white chunk, a shadow, and
the shadow on the ball
very much
becomes its own object.
Fortunately, these patients do eventually learn how to perceive objects, thank goodness. And the critical element to this that they need is motion information. Once they're able to see objects moving, they're able to actually perform these tasks. And the more that they see objects move in the real world, the better able they are to perceive and recognize those objects later. So again, I'm just going to show you this same kind of task. What shape do you see without any object cues? Really can't tell what he's looking at. But as soon as this triangle starts to move around on the screen, you can identify that that is in fact a triangle. And when given the same task as before with our square and circle, again, he'll say that you can't really segment it, and it looks like 3. But once he gets this motion cue where the square starts moving around, now it's easy for him to tell there are actually 2 objects there and not 3. So motion does appear to be a really critical cue. So clearly, no training data is not enough. We're going to need something, but what is the minimum we could get away with? Could we get away with training a visual system on just one single object that's shown in front of one single background? This would be incredibly hard computationally because of something we call the statistical concurrence problem. And this is the problem where if 2 objects are always seen together or sets of features are always seen together, a statistical association learner will learn to associate those features together. The example I have here of dumbbells comes from some work out of Google where they were testing a visualization technique called Deep Dream. And they used a deep neural network that had been trained on ImageNet and then used Deep Dream to figure out what visual features had the model learned for each of these different object categories. And as you can see from these somewhat terrifying images of dumbbells, the representations that the models learned of dumbbells included not just dumbbell features, but human arms and hands, because in all of their training data, dumbbells appeared together with hands and arms. So this should be a very hard task. And we decided to give this very hard task to our newborn chicks. What we did is for the first 5 days of life, we raised them in these controlled rearing environments where the only object stimuli that we gave them in the chamber was the object rotating in front of a background. Always the same object, one single object, always the same background, one single background. So this should be subject to that same statistical concurrence problem. I'm going to take a pause here before I get into the test phase because usually the most common question that I get asked at this point is why do we use chicks? And so I figure I should address that first just for clarity because it'll also make the rest of the experiment make more sense. There are a number of reasons, but some of the primary reasons that we use chicks as our newborn animals is because they have rapid motor development. It's probably not too surprising. They have to actually break out of their own shells. So they're pretty capable when they're born, but that means they don't need to nurse and they don't need a mother figure. They can get up and explore this virtual chamber on their own. They can go get food and water, and we don't have to introduce really any confounds into the experiment by having a caregiver. But the second benefit is that chicks imprint. And for those of you who aren't familiar with what imprinting is, this is the phenomenon in psychology where young animals will build a strong social preference for any kind of conspicuous object that they've seen in the first few days of life. Obviously, for most chicks, or geeseling in this particular example, that's going to be mom, dad, brothers, sisters. But it works for other objects too. And this works perfectly for our chicks. They do form a preference for the objects they were reared with and seek those objects out, which means we don't have to use any sort of supervised training. We don't have to reward them or shock them or feed them for seeking out the object. They'll just do it, which is nice for our purposes. During the test phase, which is the next 7 days, we give them a series of test trials throughout the day. All of the test trials are 2 alternative forced choice trials. One monitor shows the familiar or imprinted object, and the other monitor shows a new distractor object. Either object can be shown from the same 360 degrees or from a slightly rotated 360 degrees, so it could be a new viewpoint. Either object could be shown from a novel or from a familiar background. And I will also note that we choose our distractor object, specifically design it so that it has the same size, the same color, the same general brightness, and it fills up about the same space in pixel space as well as our original object. If they can actually recognize which object is their imprinted object, they should prefer to spend more time with that object. But if they can't, then they might be seeking out background features. They might not have background in order to build an object representation. So here I'm just going to show you a simple bar graph. I'm just letting you know chance is 50% because there are 2 sides, and ceiling is 80%. If anybody wants to chat about that during question, I can talk about where we get ceiling. There are 4 conditions. This is pretty straightforward because each object can be shown either on a novel or a familiar background. So that gives us 4 conditions. And what we find is that the chicks are great at this task. They're performing well across all of these different scenarios, and it doesn't matter whether their original object is shown on the original background or a novel background. It doesn't matter which background the novel object is shown on. They're not going to bark at this task. And what's great about how much data we collect and how many test trials we collect from these subjects is that we can actually look at performance over time to see whether or not they're learning a lot during this task or whether performance starts off strong. And what you can see is they actually are very good at this test from day 1. Right away, they're able to perform this task really well without extensive experience seeing objects on backgrounds. And we even see that the ability is universal across all of the subjects here. I'm just showing you a gray diamond for each individual subject with arrows on each diamond. They're quite small, but they're there. All of the subjects are succeeding, which is exactly what you would expect if an ability is universal. Now, as I mentioned before, for our blind patients, in the blind patient study, obviously motion is an incredibly important component to learning object perception. So we wanted to test whether or not that's true of a newborn visual system and not just a visual system of an adult who's never seen. So we also ran a condition where a different group of chicks was reared with the exact same objects, the exact same images or frames of the objects, but this time we removed all appearance of motion cues. And we tested whether or not they could still do this task. And it turned out that much like the blind patients, they are incredibly impaired at this task right around chance performance. There's something about being able to use those motion cues through time that is really important for biological visual systems to learn object perception. A very fair follow-up question would be, okay, we know there's motion, but what kind of motion information is needed? I could probably bore you all with another 2 or 3 talks on just this, but instead I'm going to summarize about half a dozen papers worth of findings down into this one single slide to rule them all, which is that it turns out that what you need for a visual system to learn object perception is slow and smooth object motion. And conveniently, this is also the kind of motion that we see objects showing in real life. We don't see objects teleporting from here to there. We see them gradually changing or staying static, but we create some sort of object motion by moving around them that is slow and smooth. But when we have raised chicks in worlds where the objects move in a non-smooth way, or worlds where the objects move too fast, they don't learn good object representations that let them be able to recognize those objects in new, different situations and contexts. And one brief aside from our little friend Pip, he would just like to note that the training data that he needs as a biological creature for being able to learn about objects is nothing like what we usually give AI for visual learning about objects. Usually we're training these massive visual systems in AI with images from something like ImageNet, or here I'm showing different images from Caltech 256. These are massive data sets that are random collections of pictures of different objects from the same category. There's nothing that is smooth about this. And in fact, usually when you train these, you randomize the order for training and testing anyway. The order is not important. Motion across time is not important. These are nothing like what biological systems use. And that means that really the learning processes are meaningfully different than what real biological visual systems are doing. So to summarize on training data, newborn visual systems need visual experience with slowly and smoothly moving objects to learn about object perception. Let's move on to brain architecture. What kinds of visual system models should we be using here? There are a lot of theories coming from neuroscience, psychology, and vision science about what knowledge might have to be built into visual systems in order to do object perception. And in fact, the fact that our newborn animals are so good at this task right away has suggested to a lot of psychologists I've spoken with that there must be some really strong object knowledge built in. People have theorized that we might need to build in knowledge of simple 3D forms like geons, or we might need to build into the visual system an assumption that objects are 3D cohesive and bounded. Or maybe we need to build into the visual system knowledge information about objects that takes the form of medial access structures, or you can also think of these as an object skeleton of sort that's defining the shape of the object. But again, it probably won't surprise you that I'm wanting to go down to what is our bare minimum. I'd like to know what is the minimum bias that we can build in. Do we need to build any of these sorts of knowledge of objects hard-coded into the system, or can we learn them? So instead, I want to start with a very popular learning architecture probably everyone in this room knows about, which are convolutional neural networks, or CNNs. What's really nice about convolutional neural networks for our purposes, other than them being quite popular in the vision science world, is that they have to learn relevant object features from scratch. CNNs do not already have medial access skeletons built into them. They don't have knowledge of geons baked in. They have to learn it from the data. There's no explicit object knowledge built in. Now, having said that, I will give a little bit of a caveat that there's some innate knowledge of space, right? The convolutional processing is going to have some information built in about spatial relationships. And the fact that CNNs are doing hierarchical processing as well on those convolutions means that you're also building in a little bit of inductive knowledge about local relationships between the features. So it's not nothing. I just like to give that caveat because I think that's important, and we'll come back to that later. In order to test whether or not a visual system that's domain general like a CNN can do the same kinds of visual tasks that a newborn visual system can do, we're going to do parallel controlled rearing of animal and machine visual systems. And the way that we do this is, first, we run automated controlled rearing experiments with newborn chicks, and you've seen an example of that previously. Second, we create virtual animal chambers. You can see an example of one of them here, and we simulate the visual experiences from the training phase. Next, we train an artificial visual system. In this case, it'll be a CNN with simulated images from the training phase. We use self-supervised learning techniques, and we freeze this encoder, this visual encoder, after training. So it's trained only with exactly the training information or the training environments that the chicks received. Once we've trained that encoder and frozen it, we simulate the visual experiences during the test phase using stimuli presented to the chicks. So the encoder is not learning from the test phase, it's just pulling out the visual features from the test phase. And to be able to actually test that encoder, we attach a linear probe to the final layer of the model so that we can train and test the linear probe with simulated test images. We are using a k-folds analysis here, but instead of just doing it over randomly sampled images, we're actually doing it over an entire viewpoints. So we tested about a dozen different viewpoints of the object. So any given fold is actually a full entire viewpoint of that object. And the task here is simple. It's very similar to the bicycle task you've already done. which is that the chick is exposed to only a single object for the first week of life. And critically here, they only see that object from a very limited viewpoint range of 60%. So they've only seen very, very, very little of that object. Then during testing, again, it's a 2 alternative forced choice test. So they have to recognize that object versus a distractor. But the critical difference here is during the test phase, the object can be shown from all sorts of novel viewpoints that look very, very different than training. So just like how you saw with the bicycle, when it's shown from the side, it creates an entirely different set of, an entirely different image on the retina. The same is true with this object as well. And our question is, can the CNNs recognize objects as well as the newborn chicks? So what I'm going to show you here is results across 5 different learning objectives on this bar graph. Each set of bars will be a different learning objective: SimClear, Barlow twins, autoencoder, bootstrap your own latent, and variational autoencoders. And we use the same architecture across all of them for easier comparison. It's all a resonant 18 in this graph. And I've also included chance performance and chick performance for reference. And what we found is that all of these different model types were able to succeed at this task. The different bars in each cluster are just which object and which viewpoint they were imprinted to. We make sure that we're testing across, that we're counterbalancing objects and viewpoints just to make sure these results actually generalize. But all of the models perform about as well, in some cases better than the newborn chicks do. Now, a very fair follow-up question would be, are these learning objectives realistic for biological brains? They're all in some form self-supervised, but are they fair learning objectives for biological brains? And a reason why you might think that some of them aren't is that a few of these involve arbitrary computer augmentations in order to generate their set of training data. So I'll walk you through exactly what that means, but what this means is we're going to be kind of broadening up here to also talk about objective functions for a second. And I'm going to walk through this example with SimClear in particular, but this kind of computer-generated augmentation is also used in other algorithms that I showed, like Barlow twins and BYOL. But the idea here is that for SimClear in particular, you take your original image, for example, the dog on the grass, and then you create 2 augmentations of that. And those augmentations can be created through different types of operations like cropping or Gaussian blurring or grayscale, color jitter, and you combine some amount of these different arbitrary augmentations in order to create a pair of augmented images that go with that original image. The job of a model like SimClear is to use a loss function that's going to push together the representation of 2 augmentations of the same image and push those representations away from augmentations of different images so that you're creating more similar representations of all of the dog related images and more, and those should be different from things like the chair on the right. The problem is that as far as I know, I can't think of any homologue for this in actual biological brains where our brain is sitting around cropping things and turning them into grayscale in order to make comparisons. So is there some way that we can use a similar operation that's going to be based on what we know the brain does do, for example, using information about motion over time? So what we did here was incorporate temporal information into our objective function. Here we're using an objective function called contrastive learning through time. And the idea here is that it's the same objective function as SimClear, only now instead of creating these augmentations, we're letting time do it for us. This is an embodied system that's moving around and collecting images, very similar for those of you who do autonomous driving, for example. The car is creating its own set of augmentations just by moving through space and time. And instead of pushing together different computer-generated augmentations of the same image, we're pushing together representations of images that occur together in the same temporal window and pushing those away from everything else. This means that we don't have to use arbitrary augmentations. The data set is naturally augmented or naturally generated through embodiment, and it uses time as a teaching signal. And for those of you who really love the equations and want to see, the loss function that we use in particular is this one. And for those of you who don't like equations that much, I'll kind of walk it out. On the numerator, we've got a measurement for the similarity between image at time 0 and image at time 1. We've got the similarity between the image at time 0 and the image at time 2. We want these numbers to be higher. And then on the denominator, we have the similarity between image 0 and all of the other images. So once we take the negative log of this, the closer together we get those representations of images that happen in the same time window, the smaller we get our loss. Is this combination of a generic architecture and a generic temporal objective function sufficient to explain newborn performance on this task? It turns out, yes, it is. Here I'm showing a 4-layer and a 10-layer ResNet. We tried to really pare down the architectures to be as small as possible. Same results hold with an 18-layer ResNet as well, like I showed in the other graphs. But what we've done here is just train these ResNets with contrastive learning through time. And they, again, are performing as well, if not better, than chicks at this task. As I mentioned before, CNNs do have a strong spatial inductive bias. So is it possible that we could actually get away with an even smaller amount of specialized knowledge? Could we take away this spatial inductive bias somehow and get down to something that's even more generic? One way we might be able to do that is with transformers. Transformers, as you all know, were developed for language processing, but they've been used since then in different, slightly adapted forms for all different sorts of tasks, like scene recognition, action recognition, visual navigation, decision-making, multimodal learning, protein structure analysis. So this is the model architecture that's been used across a wide variety of different domains of tasks. In this case, we use a vision transformer, and I can walk you through the language of that. What we're going to do is build a self-supervised vision transformer that learns using time as a teaching signal. What that translates into, and especially for those of you who aren't quite as familiar with transformers, is that we're going to be taking our image and breaking it down into patches. We'll flatten those patches, and then we'll apply a token and a positional embedding. But note here, even though we do have a positional embedding, there's no assumption that these patches need to be close to each other in space. The positional embedding is completely learned by the model. Then we send this result through a set of transformer blocks, each of which are learning through self-attention mechanisms. And when we finally get to the end of the model with the sim-clear projection head, we're applying this contrastive learning through time loss, which again is going to push together these images that happen in the same temporal window and push apart representations of images that appear not in the same window of time. And it turns out that these transformers that are learning with time as their teaching signal can actually also succeed at this task. Here we have a number of different architectures of our vision transformer with anywhere from 1 to 9 heads and also 1 to 9 transformer blocks. Again, these perform just as well as the chicks do. And on the right side of this image, you can also see some visualization of the attention heads where we show you in the 9-head vision transformer what each of the attention heads are actually activating in response to for the original images. And you can see how each of these attention heads is pulling out different information from the image. Some are more sensitive to object features that are close up. Some are more sensitive to object features close away. Some are even sensitive to the floor of the chamber itself, but they're all pulling out different visual information to use for the task. Just to summarize here, that means that for our brain architecture, we don't need to build in a lot of information, even though we raise these animals in really sparse visual environments. This is kind of surprising because when it comes to transformers in particular, we generally tend to talk about them as being very data hungry. And that makes sense. When we think about ChatGPT, for example, we're training it with huge amounts of data from the internet. But it turns out that even though these chicks are raised in really sparse visual environments, a transformer isn't any more data hungry to learn the same task than they are. And in terms of our objective function for learning, we can use time as a teaching signal for a more biologically plausible approach to self-supervised learning. Now, the last piece of the puzzle is the body. And you might be wondering, if we're talking about visual processing and object recognition, does it really matter what we're doing with the body? And the reason that is because our goal is to create a full creature who can recognize objects, who can do object perception, and not create some sort of disembodied brain in a vat that's connected to eyeballs, which is typically what we do when we're just working with artificial visual systems alone and not full embodied systems. And I think this is a mistake because biologically, from lots of work in neuroscience and psychology, we know that embodiment has a profound effect on perception. This drawing is from a classic controlled breeding paper from Held and Hine back in the 1960s. and this crazy contraption is called a kitten carousel. I did not make up this name, but you can tell both of the cats are yoked together in this carousel contraption. One of the kittens is yoked in a way that the harness actually lets it walk around. So as that kitten walks around, the whole carousel will move in a circle. This other kitten is just in a carriage. He's along for the ride. He's not walking anywhere, but because he's yoked to that first kitten, he's going to get all the same visual experiences of this circular room as the walking cat. Literally, the only difference is that he is not having self-actuated movement through that environment. And what's wild about these results is that they then tested depth perception in both of these kittens and kittens in both of these conditions. And the kitten who's being carried in the actual carriage contraption does not build accurate perception of depth. So, for example, if an object's coming at its face, it doesn't show any sort of startle or blink response to that object. If you put this kitten at the edge of what's called a visual cliff, it only looks like a cliff. No kittens were forced off of cliffs for the purpose of this study, but if you put them at a visual cliff, most cats will not cross it. Most people would not cross it. This kitten who is raised in the little carriage walks right off it. So there's something really off about the visual perception in this kitten, despite the fact that it has all the same vision training data as its yoked kitten. And to get at this, we've started building a series of benchmarks that we call newborn embodied Turing tests, or NETs for short. And the idea behind NETs is to be able to take the full action perception loop, not just the visual system, not just the visual training data, but to actually have embodied agents in these environments that are going to be doing the same tasks as the newborn animals. I'm going to walk you through the net for the experiment that I showed you at the beginning of this talk with object segmentation and parsing of a single object from a single background. What this looks like in terms of our newborn embodied Turing test is first, we raise chicks with one object on one background, which you've already seen. That's the training phase. Then we test whether or not those chicks can recognize objects across novel backgrounds. Then we start to build populations of artificial agents. This is where we're building artificial brains and we're actually putting them into agents. And we're building these brains as deep reinforcement learning agents. Next, we take these deep reinforcement learning agents and we raise them in the digital twin of the chamber. This is the exact same experiment with the same training phase and the same test phase. So that means step 5 then, of course, is testing these artificial agents with the same test phase as well. As you might imagine, we turn off learning between steps 4 and 5. So we train them in the training phase, but we turn off learning so they can't continue to learn during this testing phase. And finally, we compare the performance of newborn chicks and artificial agents. Just a quick reminder, the training phase involves only one stimuli being shown on a molecule at a time. It says one same object being shown on one single background. And to give you a flavor of what this would look like for the agent, you can see some of the images that our agent actually acquired during the training phase at the bottom here. So you can see what it looks like in an actual chamber. It is a bit of a different experience when your agent's embodied. And during the training phase, we do have to train them with a reward since these are deep reinforcement learning agents. And we wanted to use a reward that was reasonably biologically inspired, that would really orient them toward that object. So we used what we call an imprinting reward. The idea here is that it's rewarding to see mom or whatever you've imprinted to, right? We know that's true for actual chicks in the wild, that it's very rewarding for them to spend time with their imprinted object or imprinted mother or siblings. And we do this by rewarding them specifically for how much of their visual space is taken up by the object. So I've just given a couple examples here where you can see about what the reward would be. If the object was taking up their full visual field, so they were very close to the object and looking at it, that would be a reward of 1. If the object's taking up just a slice of the visual field, as you can see in this example on the left, we give that a reward that's just a proportion of how much of the visual input is being taken up by a bounding box around that object, which in this case comes out to around 0.16. If they're not looking at the object at all, it would be a reward of 0. Even if they're pretty close to it and looking away, it's still a reward of 0. Then during the testing phase, as I mentioned before, we're going to be testing them on whether they can recognize the familiar object versus a novel object on different backgrounds. I'm going to walk out these test conditions for you just so eventually when I show you the results, they make a little bit more sense. The easiest test condition here is where the familiar object is shown on a familiar background and the novel object is shown on a novel background. There's really not much of a challenge to this test condition because all you have to do is find familiar stuff. It doesn't matter if it's background or object. The hardest task here is when the familiar object is put on novel background and vice versa. This is really hard because a lot of the visual features that you're experiencing are background features. So if your representation of what you've imprinted to has a lot of these background features baked in, you're probably going to be below chance on this task because there's so many tempting background features. And the next two, we kind of control for the familiarity of those background features. We've got both on a familiar background and both on a novel background. And then below, of course, you can see the sample images from the test phase as well. So based on that, if these models are unable to parse, we should still expect good performance in that first easy condition. And we should expect really bad performance in the hard condition and somewhere around chance when we control for the backgrounds. Maybe they might do a little bit better than chance because they are getting familiar object features. And if they're able to parse, performance should be strong across all the conditions. And as a reminder, that is what we see for the newborn chicks. The newborn chicks are great across all of these conditions. We started off with the simplest agent that we could come up with, a very small 3-layer encoder attached to a single linear policy network that's using proximal policy optimization PPO. And the results look exactly like what we would expect if they're not actually segmenting the objects from the background. Just to orient you here a little bit, the bar graphs themselves are probably pretty obvious, but some of the other pieces that might not feel as clear, the individual dots are individual chicks or individual agent chicks, artificial chicks. And these red ribbons show us where the chick performance is. So that's where we want performance to be getting up to, is these red ribbons. We thought, well, maybe we just need to train it longer. It's possible that we just didn't train it enough, even though it looks like we did in terms of our reward graphs. So we trained it for longer and found the same results. Then we thought maybe we need a larger visual system. 3 layers is really, really small, and we've got great results in our disembodied network with networks that are a little bit more medium in size. So this time we tried an 18-layer CNN, and the results looked exactly the same. We also got advice from a colleague, look, motion information is really important. This temporal information is really important. I think that you need some sort of recurrent processing here. In order to pick up on this temporal information, you need to incorporate long short-term memory or some other kind of recurrent processing. So we used an LSTM policy network here, and the results look the same. I'm only showing one of them, but we actually used LSTM across all of these different encoder sizes. The results all look like this, spoiler alert. Then we had an idea. What if we could take some inspiration from biology? What our eyeball is doing before information even gets to our visual system is it's actually acting as a filter for our visual information. We do take in brightness values through our rods and cones in our retina, but ultimately that information gets passed to an area, a set of cells called retinal ganglion cells. And what those are actually activating for are change events. They fire in response to brightness change, not just brightness itself. And this is really interesting because if you're only firing, if you're filtering out only things that are moving, you can take a movie like I have on the left, and this dynamic visual sensor that's only sensitive to these dynamic changes in brightness pulls out the image for you right away. So we thought maybe what we should do is we should give this kind of a retinal dynamic vision pre-processing as a step to our agents. So they would take in the regular visual inputs, they would do this retinal filter step, and then send that through to the rest of the network. Again, the encoder and the policy network. And it turns out the results still look the same. We were really excited about this one. This is a very disappointing result for us. We also thought about these disembodied visual systems that we had trained before that seemed like they were really successful. So we thought, well, let's train one of those in this environment. So we'll take this network that's using contrasted linear time. We'll just freeze that. We know we're getting good features. We know that our linear probe can pull good features out of that. So let's use that. And the results, again, still look the same on this task. So we're starting to wonder at this point, what is going on here? Is there something weird with our encoders? Although we think this encoder is fine from our disembodied work, we're using very, very simple policy networks, although we also tried transformer policy networks too, spoiler alert, also looks the same. But what's going on? So one of the things we did was we decided to look at our encoders here, and we created what's called a TSNE. A TSNE, for those of you who aren't familiar already, is a way of taking this high dimensional space. So our encoders are already producing a high dimensional 500 plus feature embedding. And then we're gonna push that into a lower embedding space so we can visualize it. So we're basically dimensionality reducing it down to 2 dimensions so we can see where all of these pictures are in space. This one is for our contrastive learning through time one in particular. This is probably not very legible to you, especially folks in the back can't tell which image is which. So each different point on this is a different image. I'm going to color code it so that your eyes don't have to burn from trying to process this. Same data, but now we've got color coded where red and yellow are background 1 and objects 1 and 2 respectively. Green and blue are background 2, objects 1 and 2 respectively. Purple and black are background 3, objects 1 and 2 respectively. And what I noticed when I pull this out, and I've looked at this with all of the other encoders as well, and I think some of the other ones are even more clean than this, but what's true across pretty much all of them is that the clusters are by both background and object. And what's interesting about that is that if you do use a linear probe, it actually should be possible with a linear classifier or linear probe like this to be able to grab the right objects. This should be possible, right? So as long as I know where to draw the right lines through this space, as long as I have, a linear probe with enough neurons in it, I can still pull out object 2 reliably, or I can still pull out object 1 reliably as well. But it's not clear at all how a self-supervised classifier, how a self-supervised policy network is supposed to know which relevants are relevant to each other in a space that looks like this. So it's still very much an open question for us in our book of how do we need classifiers that are just doing a better job of moving these representations farther apart and not being based on backgrounds? Do we need policy networks that are doing a better job of looking within the space of just things without background 1 or just the space of things with background 2? I think this is an open question right now, and it's one I'm really excited about because we've made our nets publicly available, so you too can actually go on to GitHub and find this net and try it yourself. I hope some of you will. I hope some of you will get great results because we know that there are a lot of different models out there. We can't possibly test them all. We're just one lab. We're hoping other people will run with this and we'll find solutions even when we can't. And to give you a little bit of inspiration along those lines, I asked each of my grad students who I'm working with what they think is the missing ingredient. And you've already heard me talk for long enough, so let's hear what they think. Oh wait, I forgot. We don't have sound coming through. That might be tricky. It might be tricky without sound. We can do this.
I think we might need more sophisticated policy networks. Transformers have revolutionized
Sadly,
machine learning.
Technology is not cooperating with me right now, so I'm going to walk you through a little taste of the sorts of things that they're working on to follow up on this. The first grad student here is Manju Garamella, and she's been working on using transformer policy networks to be able to use more powerful policy networks on that side of things. And she's also been working on incorporating models that are encoders and specifically are sensitive to motion and segmenting objects by common motion through time. Bhargav Desai is a new addition to our lab, and he's working on building a ragdoll version of our agent. So as you saw, the agent before kind of looks like he walked off the movie WALL-E. He's not fully articulated. Bhargav is working on making a fully articulated chick model that will have a full action space that has to be controlled by our models. There may be something about using a full space of a full action space, a raw action space, the same way that there's something important about using the raw pixel space in images when we do vision processing. Lalit Pandey has been working on, has been doing fantastic work on all of our disembodied work with just visual system. And he's been finding incredible results about how prenatal retinal waves that occur in all sorts of animals, humans, chicks, rodents, primates, how those waves of activation that are spreading through the visual system prenatally before we're even born are able to set up visual systems to already have quite a bit of object knowledge before we've even experienced any real world visual input. And finally, Jake is working on a physical chamber and a virtual chamber for testing information seeking in newborn animals. What kind of information are they seeking out to create their own curriculum for learning about the visual world? And that's always a nice spot to be able to say thanks to the lab, Bhargav Desai, Manju Garamella, Zachary Laborde, Joshua McGraw, Denizan Pak, Lily Pandy, Jake Peacock, and my co-PI and longtime collaborator, Justin Wood. You can learn more about our work at buildingmind.com. But I did promise you a recipe for object perception at the beginning of this talk, so I'm going to leave you with this recipe card for object perception. You're going to start with the ingredients of embodied data that features slow and smooth object motion. You can then add in a domain general brain architecture that doesn't have strong inductive biases built in or a lot of object information hard-coded into the system. Next, you add time as a teaching signal. And finally, we know you've got to be adding something important here about your body and your action selection, but we're still actively working on this problem, and we hope other people will too. Our directions are to start generating and processing visual and motor experiences immediately, not waiting until childhood or adulthood like a lot of the benchmarks that we typically use do, but really starting to think about learning from the beginning of life, from the beginning of visual and motor experiences. Thanks, everyone.
So we can start the question. We can start with the first question. So there's a lot of progress right now in machine learning on language and language modeling, and you seem to look at the angle of visual perception. So do you think that intelligence is shaped from a visual stimuli at first, or how much of our intelligence relies on the language modeling?
Oh, that's great. So for anybody who didn't hear, the question was about how much of our intelligence and knowledge is shaped by vision versus something like language. Obviously, I work with chicks, which is a non-verbal species, as all of our non-human species are, even when they do have some basic words or language communication. It's not what we think of as full-fledged human language. So obviously, intelligence is very much possible without any kind of language. In terms of whether or not visual processing is the primary keystone really of intelligence, I actually think it very much varies by species. So for us, we are very visual as humans. We have very good eyesight, and we rely dominantly on our eyesight as opposed to other forms of our senses. But there are other animals who rely a lot more on olfactory information or a lot more on auditory information. And for them, those modalities might actually be arguably the most important, but my sense is that they're able to apply a lot of the same learning mechanisms across each of these different modalities, and all of those have to get integrated together somewhere. Probably for those of you who are more into the neuroscience nerdy side of this, the entorhinal cortex and hippocampal area would be where they would all get integrated, among other places. So from that sense, your dominant perception could vary from species to species, but the way that they're processing that information probably shares a lot of commonality across species. It's just a matter of how much processing are they doing, how much complex processing, and really how much of the cortex is dedicated to that.
And you also have one slide, I think it was right before you introduced contrastive trials, where you were showing you were talking about data augmentation, right? Mm-hmm. So I have a question here. So what if you take a network and just don't do any data augmentations? Well, would this kind of bar be that, right? Because, well, you can take just standard CNN, right? And you don't have to necessarily do any data augmentation, right?
Yeah, when you say if you don't take any augmentations, I can interpret that two ways. So I just want to double check. One way that I could interpret that is with a type of learning objective that generally doesn't include augmentations, like an autoencoder. But one approach to that would be to take something that usually uses augmentation, like sim clearing, that we talked about a lot, and then take the augmentation out of it and just say, I'm going to push everything away from this image, just without the augmentation angle. Is that?
Well, the first, I think the first scenario was I was thinking about, right?
Yeah. I think that's really interesting. I'm very, very open to the techniques that don't use like autoencoders, for example, that don't use augmentation at all. We've actually been using, obviously, as you
I mean,
said.
I presume the performance would be worse, right?
Yeah, so we've tested and kind of a non-dynamic level, we've tested, as you saw, autoencoders and variational autoencoders, and they do okay, they're not as good, but they still can get by at this task. They have kind of very interesting learning curves that we can chat about later if that's interesting, but we've also been on the dynamic side trying to take time as a temporal cue. We've been using masked autoencoders, masked video autoencoders on the transformer side. And some of the tasks they're okay at, and some of the tasks they really aren't nearly as good as our contrastive learning through time transformer, which has been really interesting to us. So I don't want to make a strong stance on that since we're still in the early days, but we've at least been having a lot more success with our contrastive learning through time version of SimClear with both our CNNs and transformers than we have been having with the masked autoencoders. Really.
Just a last question, because before I let somebody else do it. So it seems that across all your experiments, networks are usually performing significantly better than the chicks, right?
Yeah.
What's the reason for that? It's just like, I mean, the trials are fairly designed in such a way that the artificial agent is exposed to exactly the same condition as the chick experts.
That is a very astute question. She asked why it looks like at least for just the visual system, it looks like these visual systems are performing better. And a lot of that is because the way I'm showing data here is the most standard way in the field of looking at the performance of these self-supervised encoders, which is to use a linear probe. So we use that because that is the most standard. But if you think about it, it's not clear that that's the most fair way to compare this to the newborn chicks. So in order to have our linear probe, we still do have to do supervised training of the linear probe. And we're using k-fold analysis. So that linear probe gets trained with multiple different viewpoints. It still does have to be able to extrapolate to generalize to a completely novel viewpoint it's never seen before. But that's still a lot more visual experience in a way. So in a way, it's not fair. So to get around that, in the same paper, we actually have a lot that I didn't get into here, where we have one version where we use a k-fold analysis where we train on just a single viewpoint and test on all of the left out. So it's almost like an inverted k-folds, if you will. And performance is still good, but it is much more similar to chick performance. And then we have also a version of kind of unsupervised, I want to call it sort of like a self-supervised way of probing these, where instead of using a linear probe, we take kind of an autoencoder approach and look for how well it's able to reconstruct the images as a measure of how close or how similar it is. And so we use that as well. And again, not as good as these supervised probes that I showed you here, much closer to chick performance, successful, but very much closer to actual chick performance. So it's really smart that you learned about that. Yeah, it's exactly the right question. Yes.
What is the resolution of the images that you're feeding to the artificial, to the artificial model? What is the biological significance of that resolution? Like, is that the same resolution that the chicks see?
Oh, what a beautiful question. So you're asking about the resolution of the images in the just visual system. I believe we're using 256 by 256. We downscale it a lot for the RL just to make it tractable to run a little bit easier. For our servers, and that we actually scale down as low as 64 by 64. I don't have a great answer for exactly how it would map on, because nobody's really done the exact comparison between pixels per inch and exactly the way that acuity works, but it's worth noting that acuity of chicks is, to be fair, much lower than acuity of humans. So using some of these images where the resolution isn't quite as high does seem like it's a reasonably fair move, but nobody's really made that one-to-one distinction between, is it more like 64 by 64? I wish somebody had. I think it'd be a really interesting analysis, but at least I don't know of anything published where people have made that attempt. It's a good question. And who knows, maybe that's also an interesting way of accounting for potential differences in some of our work that's just visual system versus embodied.
Okay, so you mentioned that the policy models are having trouble generalizing to different backgrounds. So do you think that's more because the models are learning to associate rewards with the areas of the background around the moving objects, so it's failing to draw the object out? Or like, could it also be because maybe the models aren't learning to like rotate their vision towards the object when they're not familiar with the environment of the new background?
Can you say the last part one more time? They're not,
Sure.
rotating, sorry.
So it's, I mean, the model has like kind of seen the full layout of the original background, and so it like, in that picture of the road, it might see, okay, the mountains are over here. Oh, I know the object is right there, I can just rotate towards it. But in like a jungle environment, it sees trees, it's like, I don't know where the object is relative, I don't know to move left or right to find the object.
Oh, that's interesting. That's interesting. Well, I'll preface this by saying any answer I give is a little bit of speculation, since it's still an unsolved problem. I think what's happening here is when we look at the types of representations that these encoders are building, and this is even true of some of our, encoders that perform quite well with our linear probes, they can disentangle the objects, but they do still seem to be entangled by things like background. And one of the things I didn't actually show here is that you can still actually, I will show it. This is not the background one, but this is the study with just the object being recognized from different angles. The input of this encoder that's still quite successful is clustered not just by object, but also even where you are in a chamber. So, and this is reasonable, right? I mean, if I were to take your visual information right now, it would be terrible visual information if I could not pull out the fact that you're looking at me, but if I also couldn't pull out that you're sitting here. It's so useful for you to know I'm about this far away, I'm not right up to her face, I'm not in a different room. We want this information to be something that we can pull out of the models, but I think right now we're working on just figuring out which information, if it's all baked into this, which information do we pull out at which time for which task? And that I think is the real question. Yes.
You mentioned the situation is extremely hard, and it would be quite unfair to start with a pre-trained policy, right? But then, if you think about it, like chicks weren't born randomly. They evolved for like, I don't know, long time. Maybe they're already pre-trained to know the world, know about the reward. Like they gotta know, they gotta move first and see something and imprint. So wouldn't this be a little unfair for the machine because they are initialized randomly with noise?
This is such an interesting question, right? So there's a lot baked into this question that I think is really interesting. One is this question of maybe there is some sort of information that's hard coded in that we would eventually need to hard code into the models. I think that's a really fair question, and I think it's a question that we can't ask without building models like what you're saying, where you do hard code in some of that knowledge and see. I will say that for the, let's see if I actually have this in here as well, for our, oh, it might not happen in your tracks. For the background segmentation, we actually did test a number of completely pre-trained popular encoder models, and all of those perform the same way. But it's an interesting question on the policy side. What if we do need to bake in something? And the closest thing we do to that is kind of baking in the knowledge of imprinting, baking in the knowledge of like seek out this big conspicuous thing and like that. So we've done that a little bit. The question is, what does it mean computationally to actually write that into the system? But I think there's another really interesting point there about what you're saying, which is, if I may sort of unravel it even more, which is how do genes end up writing this in? Are they written in as hard-coded connections, or are they written up as a set of prenatal processes? And so this comes back to some of the work that one of my grad students is doing that I mentioned in passing with some of the prenatal training. We know that there are actually waves of spontaneous activation. And I mentioned it in terms of the visual system, but it's actually happening in the motor system as well, where there are waves actually of motor activation through motor neurons. You see babies kicking in utero and everything. I mean, that's part of what's happening is there are these waves of motor activation that are happening, and those can still train up the system. So I think there's a really interesting question there too about how we could incorporate prenatal training and how that might actually create some sets of knowledge and maybe even interesting policy networks like you're saying before the chick even opens their eyes and before we even put the agent into that environment. And I think that's such a beautiful question for future research. Oh, yes.
What if we were only showing one object to the chick with different angles, right? What if we have like 10 or 20 objects, and what do you think the difference between chick performance and models of comfortability.
So if training were with many objects?
Yeah, like let's say you cannot many objects.
Oh, that's interesting. I mean, our chicks hit ceiling right away for just one object, so I imagine the chicks would actually be quite good at it. I would suspect they'd be better. The only reason why they might not be from a very kind of not necessarily as computationally interesting perspective is that that's a lot of objects to imprint to, so it might be harder to get them to imprint all 20. In prior studies of control varying chicks, I've never really seen anybody try to imprint chicks to more than maybe 3 objects. So it's not something that's been done yet, but it could potentially be possible to imprint them to that number of objects. It's just something that has to get tested. It'd be really interesting to try that. Yeah.
Also, the chick would be moving in the environment, right? While models only see a static version of an image.
The chicks are moving, and our models all do see that movement as well. So even when we just do the visual system training, we still actually do have a chick agent. We just drive it around the chamber to get different views. So they still do see the whatever it is we've got up on the screens from far, from close, from the side. They're getting all this that same stream of their body feedback. Oh yes. Okay.
What do you think the role of social embodiment might be? So chicks are not usually only children, so how much of what they learn is mimicking what they see other people doing?
Oh, what a great question. And what I'll say before I even answer that is that we're actually looking to test that. So we just are almost finished, building these new chambers in our lab where we're actually using very large screen televisions. Oh, none of these are screen. But they're incredibly large so that we can actually fit many chicks into one chamber at once and raise them all together and look for how that influences it. So while I don't have a fully satisfying answer to that yet, I'm hoping that soon I will have a more interesting answer to that. But I think that's fascinating, right? This question of social learning and imprinting for chicks is a really important key to how they're even able to do social learning, because by imprinting and having that preference to go towards their conspecifics, that means that they're seeking out new environments that they maybe wouldn't otherwise, and then they can learn also from those other chicks what to do in different scenarios. But having said that, I think it's fascinating that even with these chicks that are reared completely on their own, with just virtual objects, still learn how to eat and drink. I mean, in a way that's sort of fascinating since they can never watch somebody else eat or drink. How do they figure out to eat the food and not eat the floor? I guess I've never watched them closely enough to see if they try to eat the floor, but somehow they're able to figure that out, which kind of speaks to this question about maybe some form of built-in knowledge in the system for what is edible or what they should be doing. But I suspect that what we would see through social learning is an explosion of learning, right? Because now you get to learn from not just social cues, but you get to learn through the group dynamics, and you get to take advantage of knowledge that others have that you don't, which could be really, really useful for building even more robust object perception abilities potentially.
Well, let's thank the speaker one more time.
Other ones?
Thanks, everybody. Thank you so much for coming. That's really exciting research.
Yeah, you learned from that.